complementary potential energy in the same way as what we did for the total potential energy. We define this quantity in terms of statically admissible stress field. Okay, so we define in this way. So pi c is simply the combination of UC and WC, and UC here is simply the complementary part of U that you saw before. So this is the complementary strain energy. Okay. You know how to define the U bar C, right? U bar C is simply the area under the curve with respect to the stress axis. Okay. So now we just simply perform that U bar C, which is a function of stress. Okay. We perform the integration of that quantity over the whole body. So we define this as a complementary strain energy. Okay. Whenever you take or whenever you introduce the statically admissible stress to the body here, now you can get U bar C because the material is hyperelastic, so U bar C exists, right? So then you can compute U bar C, okay? Whenever you know sigma, you plug it in here. Now you perform the integration, you can get UC, okay? And the second part, we can define this is the complementary load potential. Okay, you can think about this as what? The work done. Okay, the work done due to the traction that generated on that side. Okay, the traction that generate on that side is simply sigma ij multiplied by nj. You can think about this the reaction traction, right? So it's the traction that generated on the surface that you know the displacement field. Okay, you take that traction and multiply by the displacement that you know here. Okay, that is simply the work done due to the reaction, right? Okay, and then you take the negative of that quantity, you call that complementary load potential. Okay, so if you look at the definition here, you can see that whenever you are given stress sigma that is statically admissible, you can compute pi c easily by simply plug it in the formula that I show you here, right? Is that clear? Okay, you plug in sigma in this expression and perform the integration. Now you get UC, and you take the product between the given sigma and n, you get the reactive traction here and multiply by the prescribed U0. Now you perform the integration on that surface SU. Now you get this quantity. Okay, you get WC. And then you combine them, you get pi c. Okay, so pi c is simply a functional that map any function sigma to the real number. So what you will get if you plug in sigma into the expression here, you will get a real number. It can be positive, it can be 0, or it can be negative, depending on sigma. Okay. Now, what I mean by pi c is stationary at sigma. We define the stationary condition of the functional pi c in the same way as we did before for pi. Okay, so basically pi c is stationary if the first variation of pi c vanishes at that sigma. Now we can say that pi c is stationary at sigma. Okay, the first variation have to be 0 at that particular value of sigma. Okay. Or if you would like to express that condition mathematically, this is what I mean by that. Okay, the first variation of pi c is simply, the first variation of pi c can be computed based on the derivative of that function, derivative of that function with respect to h. And then you plug in h equal to 0. So this we call the first variation. So the first variation vanishes at the stationary point. It's simply this condition is satisfied for every choice of delta sigma. Delta sigma here is simply what? The perturbation of the field sigma. Okay, make sure that sigma plus h delta sigma still sit in the set of all statically admissible stresses. Okay. For linear elastic materials, we can prove that the stationary condition that we have here is equivalent to the minimum condition of pi c. Or I can say that for linear elastic material, pi c is stationary if and only if that sigma produce the minimum value of pi c, or the point, the stationary point, is simply the minimum point for pi c. The two conditions here are equivalent. Okay. Typically, we will not use the term stationary for the linear elastic case, which is simply replaced by minimum condition. Or we can say that the pi c is minimum at that sigma. Okay, so that is the same as saying that pi c is stationary at sigma. This is valid only for the linear case. Okay. Now let's look at the final technical term that we say that sigma is the correct stress field. If you remember, if you look at the formulation that I show you for option 3, right? That we formulate the problem in terms of stress field. Okay. If you look at that case, you know that okay, stress is the correct stress field if what? It satisfies equilibrium equations. It satisfies stress compatibility condition, and also satisfy essential and natural boundary conditions. If all these conditions are satisfied, now we say that stress is the correct stress field of the given problem. Okay, if you remember, okay, look at the homework assignment number 1. I also asked you to formulate the problem in terms of stress, right? If you remember, the key governing equation for that case is equilibrium equation and stress compatibility condition that we call Beltrami-Mitchell equation, right? And also the two boundary conditions that have to be satisfied. Okay. So if you want to verify that stress is a correct stress field, all these conditions have to be satisfied. That's what I try to say here. Okay. So this is the classical condition that we use to check that stress is correct stress field or not. We check all this condition. Okay, now if we go back to look at the statement of the principle, now you can see that the principle here allow you to replace this kind of condition, right, by the stationary condition of the total complementary potential energy, right? The two are equivalent. Is that right? Because this principle says that, okay, if you look at a set of all statically admissible stress fields, the one that produce pi c stationary is the one that is the correct stress field. Okay, the one stress or sigma that produce pi c stationary is the correct stress field. So now if you want to verify that stress is the correct one, you don't need to check all these conditions. Okay, you just simply verify that pi c is stationary at that stress. Now you can say that stress is the correct one. Okay, in this sense, it's allow you to reformulate the problem again in terms of stress without using this classical condition. You can use the condition we have here that related to the stationary or minimum condition for pi c. Okay, Okay, this is what I try to mention to you. We can replace equilibrium equation, stress compatibility condition, and all boundary condition that we have. When we try to formulate the problem in terms of stress field, we formulate in terms of these two governing equation and the boundary condition, right? We can replace all this by the minimization of total complementary potential energy functional or pi c over a set of all statically admissible stresses. Okay, so we can replace all the classical condition by the minimization of pi c over a set of all statically admissible stresses. Okay, is that clear? So this is what we have for the U bar C. U bar C is simply 1/2 Sij/KL sigma ij sigma KL, because we focus only on linear elastic material. So I change the stationary condition to minimization because we focus only on linear elastic material. Okay, so now we have the boundary value problem option 3. This is the modified one, modified by replacing equilibrium, stress compatibility condition, and all boundary condition by the minimization of pi c. So this is the new formulation that I have. I still choose stress as the key unknown, but the governing equations change to what we have here. So now if you want to get the correct stress field of the given body, you just simply minimize pi c. Okay, you try to minimize this pi c with respect to stress. And the set that you deal with here, stress have to be statically admissible. Okay, stress have to be what? Sufficiently smooth and satisfy equilibrium condition, and also satisfy traction condition on the surface ST. So then we call them statically admissible. Okay, so now we try to single out an element from that set. Okay, that make this one minimum. That's gonna be the correct answer. Okay, is that clear to you? Okay, we're done with this principle. I will not prove the principle, but I will show you that, okay, I will show you here that the principle can be applied to reformulate the problem again in terms of pi c. Okay. Now we can move to the last theorem, what we call reciprocal theorem. Okay, some of you here may be familiar with the theorem before because you applied this theorem in the proof of the symmetry of the matrix K on the matrix F. Okay, if you remember, Ajahn Savekshai used to prove the symmetry of the flexibility matrix, right? We can prove that using reciprocal theorem. And also the symmetry of K can be proved using this theorem again. Okay. Reciprocal theorem that I will show you here can be proved using the principal virtual work or the principal complementary virtual work that I mentioned to you before. Okay, so I will not prove it here. So if you know the principal virtual work and the principal complementary virtual work, you can use one of them to prove this theorem. Okay. For this theorem, we just focus only on the body that made of linear elastic material. This is the key point. Okay, and this is also the limitation of the theorem as well. The reciprocal theorem cannot be applied to a body that made of nonlinear material. Okay, it's applied only to linear elastic material, the body that made of linear elastic material. Okay, stress-strain relationship have to be linear. Okay, so it's quite limited in terms of the scope of the theorem, right? Compared with the the first two and the third and the fourth one that I showed you before. Okay. Now look at state 1 of the body. Okay, let's look at the state 1 here. So let's look at the body that's subjected to the body force field B1, the traction on the surface. Let's say that, okay, for the entire battery, we know the traction T1. T1 here is the prescribed traction on the battery, on the entire battery. Okay, we don't have any part of the battery that we know the displacement. Let's say that T1 is the traction that apply for the whole battery, and B1 is the body force field. Okay, let's say that this is state 1. Okay, let U1, epsilon 1, and sigma 1 be the solution of the displacement, strain, and stress for this state 1. Okay, now I look at the same body, but I apply the different set of body force field and traction on the battery. I look at the same body, the body that made of the same material, the same shape, everything are the same, except that, okay, I change the external loading condition. Okay, this body now is subjected to the body force field B2 and the traction on the battery T2. The rest, they are the same. Okay, now for this state 2, let's say that I can get the solution of this state. U2, epsilon 2, and sigma 2 be the displacement, strain, and stress of the state 2 due to the applied force B2 and T2. Okay, we have 2 states associated with different set of applied forces. Okay, the first state is associated with B1 and T1. The second state here is associated with B2 and T2. And the solution for each case is denoted by the quantity with the superscript 1 and 2, respectively. Now, the theorem just says that the 2 equations here hold. Okay? Look at the first equation. If you take the body force from the state 1 multiplied by the displacement from state 2, and you take the traction from state 1 multiplied by the displacement on the battery of state 2, and you perform the integral over the battery and over the body. Okay. Okay, if you take a look at term on the left hand side of the first equation, that is simply what? The external work done due to the body force from the first state and the traction from the first state through the displacement from the second state. Okay, if you look at term on the right hand side, we do in the opposite way, right? We take the body force field P2 here, multiply by the displacement from the first state. And we take the traction from the second state, multiplied by the displacement from the first state, and we perform the integration over the body and over the battery. And we can see that we can prove that the 2 quantities here are the same. Okay? And if we look at the second equation, if we take stress from the first state, multiplied by strain from the second state, and we perform the integral over the body. And term on the right hand side here, we take stress from the second state, multiplied by strain from the first state, and perform the integral here. If you look at the quantity that we introduce here, you can think about that they are simply what? Internal work done, right? Internal work done of stress from one state through strain from the other state, right? They are the same. Okay, so that's the theorem. So you can take force from one state to the displacement from the other state, right? And you can think about that as the work done. Okay, so if you look at the external work done, external force. Okay, the external work done from from the force from the first state due to the displacement from the second state is the same as the work done due to the external force from the second state due to the displacement from the first state. The same thing for the internal work done. The internal work done due to stress from the first state, okay, where the displacement from the second state is exactly the same as the work done due to the stress from the second state, where the strain from the first state. Okay. How can we prove this? We can use principal virtual work and also the principal complementary virtual work. Okay. I will not show the proof here. You can go back and think about how to prove this. Okay. Okay. I can show you one simple application. If you have a beam, if you have a beam like this, you have the same beam. If you apply the force here, equal to P1, let's say that it's equal to P, and I call this point A, okay? And for the second case, the same beam, I apply the same force P, but not at point A. Here, I apply at point B. Okay. The first case, I apply the force P at point A. Now I look at the point B, the same point that we apply the force for the second case. Now, I compute the displacement. Okay, let's say that I record VB. VB is the vertical displacement or the diffraction of the first beam. Okay, I put the superscript 1 here. Also, when I look at point A for the second case, I apply the force P at point B for the second case. Now I record or compute the vertical displacement at point A for the second case. Can you conclude about VA and VB here? VA2 and VB1. Do you think they are the same or they are different? You may be able to answer this based on what you learned from structural analysis class, right? Can you tell me about the relationship between VA2 and VB1? Are they the same or what? If you apply the reciprocal theorem, you can see easily that if you compute the work done due to the force from the first state via the displacement from the second state, okay, you can see that you take the force from here, it's simply P multiplied by VA2. That is the work that I talk about. The same thing, the same way, I compute the work done due to the force from the second case, where the displacement is generated in the first case. So it's simply P multiplied by VB1. And the two quantities are the same, right? Based on the first equation that I got from this theorem. So P VA2 have to be equal to P VB1 and P cancel out. So now we can conclude that VA2 and VB1 are the same, right? And this kind of things can be used to prove the symmetry of flexibility matrix. If you go back, right? The flexibility matrix is symmetric because of this kind of properties. Okay, this is one application that I can think about. Okay, the other application that you learned before, for example, you try to sketch the inference lines, right? The moving load, when you try to get the response of the structure under the moving load, you can apply this principle as well. It will make the problem simpler in some sense. Okay. Do you have any question about anything here? มีคำถามอะไรไหมครับ Okay, I'm done with this lecture. Okay, I show you all 5 common or well-known theorems that you should know in solid mechanics. The first 2 are the most important pair. You know, the first 2 equations and the first 2 principles are most common and important theorems. Okay, because you can use the 2 to prove the remaining theorem that I show you here. Okay, go back and try to digest what I mentioned and prove on whatever the detail that I mentioned in this class. Okay, try to understand and the application of the theorem that you used before. Maybe you cannot recognize what you applied before, but if you try to connect to what I mentioned here, you will see. Okay, I have one example, okay, at the end here. Okay, actually this is the homework assignment several years ago that I asked I asked the student to solve. Try to prove the principal virtual work. Okay, if you have time, you can study this because it will be useful for for solving the problem in assignment 2 as well. Okay, here I just look at the body. Okay, let's say that, okay, I have a body omega, and the body here is subjected to the body force field B. Okay, and also the traction T0 on the entire battery. In this case, I don't have any portion of SU. I don't have any portion of the body that the displacement is prescribed. Let's say that, okay, at every point on the battery, we know the traction equal to T0. Okay, let's say that, okay, the body that I consider here is in equilibrium. So this is the condition that I gave you. If the body omega here is in equilibrium with the applied force B and T0. So that is the condition I gave you. Let's say that the body that I look at here is in equilibrium. Now I want you to apply the principal virtual work to show that all equations here are correct. Okay, it's similar to the first problem in the second assignment, right? Because you know that the body is in equilibrium, and now you try to use the principal virtual work to prove something. Okay, it's similar to, if you think about it, similar to the first problem. How can we prove these 3 equations? You have to choose the appropriate choice of the virtual displacement, right? If you remember, the equilibrium and equation of virtual work equation are equivalent, right? So the principal virtual work just tell you that equilibrium condition of the body and virtual work equation are equivalent. Now I know that the body is in equilibrium, so it implies that the virtual work equation is satisfied for any choice of the virtual displacement. So if I pick the appropriate choice of the virtual displacement, I can prove all 3 here easily. Okay. We are run off time here. Do you have any class after this?
No, Ajahn.
Okay, so let me continue for 5 or 10 minutes. So you will see the example, how to guess the displacement field. Okay, how to shoot the virtual displacement. Okay, let's look at the first case. Okay, if I want to prove this equation. So if you look at this equation, it's simply the overall equilibrium, right? This is the overall force equilibrium. So the integral of BI dV here is simply the net force due to the body force. And the integral of TI0 over the boundary here is the net force due to the traction. So the two here, when you combine, have to be 0. So this is simply the overall equilibrium of the body. The overall force equilibrium, right? Or the net force have to be 0 because the body is in equilibrium, right? You know that this one is true based on the second law of Newton, right? You know about this. But now I would like to show this using the principal virtual work. How can I do that? Okay. Now, since the body is in equilibrium, the principal virtual work implies that this equation is satisfied, right? Because the body here is in equilibrium. So this virtual work equation is satisfied for every choice of admissible virtual displacement. Okay, this is satisfied for all admissible choice. Okay. Now, if I choose delta ui equal to ci, ci here is a component of the vector c. Okay, that is arbitrary and constant. Let's say that I set delta ui equal to ci. C here is constant. Okay, it's a component of the constant vector, and it can be anything. It's arbitrary. Okay, so if I pick delta ui equal to ci, this equation is still satisfied, right? Is that right? Is that right? Because principal virtual work tell us that whenever the body is in equilibrium, this one is satisfied for any choice of admissible delta u. So I choose delta ui equal to ci. This equation is still satisfied, right? So now I plug this choice back in this equation. Before I did that, I have to compute virtual strain from the virtual displacement. But you know that delta ui is simply a constant. So delta epsilon ij is 0, right? Because if delta ui is constant, derivative of the constant function is simply 0. So delta epsilon ij is 0. I plug that thing in, I will get this. Is that right? So this one is 0, so this disappear. So I plug in delta ui equal to ci, so I get something like this. And ci is a constant, so I can pull it out of the integral. Okay, I get something like this. Okay. If you take a look at this term, someone tried to cancel ci by divide the whole thing by ci. That is wrong. You cannot divide the whole thing by ci because if you take a look at the index that you have here, this is not the free index, right? This is the dummy index. Basically, the term that you got here, you're going to get C1 multiplied by this one with I equal to 1, plus C2 multiplied by the whole thing here with the index 2, and plus C3. Basically, this one, on the left-hand side, you have 3 terms, the combination of 3 terms. You cannot just simply cancel out CI by dividing the whole thing by CI. You cannot do that, right? But you know that, okay, CI here can be anything because C is arbitrary here. And you know that the whole thing here is 0, always 0. It doesn't matter what CI is, right? Now you can conclude that the term inside here have to be 0 because this one is arbitrary. You learned this from Ajahn Chatpan, right? Because you can think about the linear independence property of CI because C1, I'm sorry, of the term here, right? This, we can think about this as a vector. So CI is arbitrary. So the term inside here have to be 0, right? If it's not clear to you, you can think about choosing C1 equal to 1 and C2 and C3 equal to 0. Now you can conclude that the term here is 0 for I equal to 1. And then you can choose C1 equal to 0 and C3 equal to 0 and C2 equal to 1. Now you can conclude the term inside here equal to 0 as well for I equal to 2. You know what I mean, right? So finally, we can conclude that this term is 0. We're done with the proof of the first equation. Is that clear to you? Okay, so we can do exactly the same way by choosing different choice of delta ui. So your friend just mentioned to just ask me at the beginning of the class that it's very difficult to choose the appropriate choice of of delta ui. I agree with you, but I cannot tell you the choice, because if I tell you the choice now, you can prove by just simply plug in the choice that I gave you. So it seems that you don't need to do anything, right? So I would like you to come up with the appropriate choice. You can take a look at the one that you would like to prove, right? If you go back to, let's say, go back to, sorry. If you go back to the second equation here, what should be the appropriate choice when you look at the one that you got here? You can see that you have bi multiplied by epsilon mk xk, right? So this somehow, if you separate this, the product between epsilon I mk and xk should be the choice, right? And the same here, you can see that. Sorry, I have a problem again with the mouse. You see that? And you need to supply one constant to the product here for the arbitrariness of the delta ui. So I will think about the product here and a constant should be the appropriate choice for delta ui, right? Okay, so now I move to the proof there. You can see that the choice that I choose here, I use the form that I got, right? I talk about this one and this one, right? That two terms appear in the equation that you want to prove. And then I supply Cm here because I need the arbitrariness of delta ui. I supply this one here, and I say that, okay, Cm here is arbitrary constant. Okay, so this is my choice, delta ui. One thing that you have to be careful, someone just meet this constant, for example, and say that delta ui equal to the product between epsilon I mk and xk. Can anyone tell me here why this one is wrong? มีใครบอกผมได้มั่งถ้าเกิดผมไม่ใส่ constant ตรงนี้ลงไปอ่ะแล้วคุณเซต delta ui เท่ากับ epsilon I mk คูณกับ xk ตรงนี้ผิดตรงไหนอ่ะ Can anyone tell me about this? If I remove Cm, I set delta ui equal to epsilon I mk xk. This one is wrong. Totally wrong. Can anyone tell me?
ตรงพจน์ ui มันมีฟรีอินเด็กซ์1ตัวแต่ถ้าเป็นพจน์ฝั่งขวาตรง epsilon กับ xk ถ้าตัดเสียออกไปมันจะมีฟรีอินเด็กซ์2ตัว
Okay, that's right. Your friend say that, okay, the free index on both sides are inconsistent. That's right. Because if I remove Cm here, you can see that on the left hand side, you have only I as the free index, but on the right hand side now you have I and M. Okay, this is totally wrong. Don't do that in your homework. If you try to pick any choice, okay, make sure that the index is consistent. Okay, so here the supply of Cm, I have two reasons. One, I need the consistency of the index, and the second one, I need arbitrariness of C to conclude something at the end. Okay, so now I choose this choice for delta ui. Now I can plug it in. This equation is satisfied again because it's satisfied for any choice of delta u that is admissible. We know that this one is admissible, right? Because you can take derivative and it's sufficiently smooth, right? Okay, so I can get delta epsilon ij easily. You just simply take derivative of that displacement field. Okay, I just use the property of the function and I perform derivative, and you can see that this will end up with 0 at the end. Okay, I just simply use the derivative of the function, right? Okay, so this end up with 0. It's not surprised that you get 0 because this one is the rigid rotation. If you remember, I think Ajahn Tirapong talked about this. The displacement of this particular form is simply the rigid rotation. So this will produce 0, this strain, okay? So delta ui of this particular form produce delta epsilon ij equal to 0. So now I can plug this thing into this equation. So term on the left-hand side disappear. So we get the two term here. The sum of the two term here is 0. And now if you take a look, Cm here is a common factor, it's constant, it can pull out from the integral, we get something like this. Again, if someone try to say that I divide the whole thing by Cm and then I get the thing inside equal to 0, that is not correct because Cm here is the dummy index. Okay, so basically you take a look at here, you have three terms. You have C1 multiplied by this with m equal to 1 and C plus C2 multiplied by the thing inside with m equal to 2 and plus C3 multiplied by the thing inside with m equal to 3. So you cannot cancel out Cm because you have C1, C2, C3. You cannot cancel them out of the equation that you got here. So the thing that you can do, you can say that Cm here is arbitrary, right? And the whole thing here is 0. And Cm is arbitrary. So now I conclude that the thing inside here is 0. You can do like this. You set C1 equal to 1, C2 and C3 equal to 0. So now you get the term here equal to 0 with m equal to 1. You do like this for m equal to 2 and m equal to 3. So you end up with the conclusion that this one is 0 for any m. You're done. Okay, this is the proof. You can do exactly for the final case. For the final one, it's easier than the second one because it's quite clear, right? If you take a look at the equation that you want to prove here, you can see that this should be delta ui, right? It seems that this should be delta ui, and term on the right hand side we can show it later. Okay, based on the thing that appear here. It suggests you to choose delta ui equal to xi, right? I have two questions from you guys here. Okay, basically it's not a question. You just answer my question. Okay, that's good. Okay, move to the last case. Okay, I choose delta ui equal to xi. Now, if you ask me why I choose delta ui equal to xi, because I look at the equation I want to prove, right? It suggests me that my appropriate choice should be xi. So now I choose delta ui equal to xi, and if I plug this thing back into this equation, it's satisfied again because this one is admissible, right? This one is satisfied for every choice. So this choice have to be, when we plug it in, this one have to be satisfied as well, right? So now I can compute delta epsilon ij for delta ui equal to xi. I plug in xi here. Xi comma j is simply delta ij. Xj comma I is simply delta ij as well. So now you get something like this, right? So delta epsilon ij is simply direct conical delta ij, right? Delta ij like this. I plug thing in. So delta epsilon ij is simply delta ij. I plug it in here. So term on the right hand side like this. You can see that the two terms on the right hand side are the same as what we have in the equation 3 that we want to prove, right? And term on the left hand side, what happened? Sigma ij multiplied by delta ij. I and j are dummy indices. And delta ij, we have the contraction property, right? For the conical delta property. You learned that from Ajahn Tirapong. So now we can contract sigma ij into sigma ii, right? Right? I use the contraction property of delta ij. So now the product here becomes sigma I. Okay, you learned this before, right? Now we're done with the proof. Okay, why don't you try to do in this way? Look at the one equation that you want to prove, and now you come up with the choice of delta UI. Okay, be careful about the index. That's the only thing that I can tell you here. I cannot tell you the choice, because if whenever I tell you the choice, you just simply plug in and you're done. Okay, is that okay, Anne?
Yeah,
I cannot answer your question.
yeah.
Okay, about the form. So you have to try until you are successful. Okay.
Yeah.
My suggestion: look at the equation that you want to prove. It may tell you something on the choice of delta UI, and also for the second problem. Okay. Let me share you this for 1 minute before I finish the session here. Okay, this, can you see this? Can you see the PDF file here?
Yeah, I see.
Okay, take a look at the problem statement here. If you take a look at question 1, now when you take a look at the term on the right hand side, you should think about how can we relate this to the term in the virtual work equation. We have TI0 and it multiplied by, we have 1/2 here, and this is xj. The problem here, the index here is j, not I, right? So now you have to think about how to play around with that index, and if you think about this, okay, you don't have the body force field here, so the term associated with body force disappear. This is the term that you have associated with the traction applied on the battery. Okay, if you take a look at the external work done, you can think about this, the external work done due to the applied traction T0. Okay, what should be the virtual displacement that gave you this as the virtual work done, the external work done? Okay, the same thing here. If you think about this, if you compare this with term on equation, a complementary virtual work equation, try to think about you have UI0 here multiplied by normal vector. So the normal vector here somehow related to the choice of delta U. The choice of what? Stress, right? Or the traction, because this have to be related somehow with the traction that produced by the virtual stress that you choose. And you have N here already, because to get the traction on the battery, you need to multiply by normal vector, and N appear here already. So now you have to think about what should be stress that will produce the traction like this, and then this will be the term that we call complementary external work done. Okay, that's the only thing that I can give you here. Okay, you can try. Do you have any question about anything else here? มีคำถามอื่นไหม Okay, if you don't have any question, I will stop here. I have to apologize that I take you more time here. Okay, so if you don't have anything else, I will see you again on Thursday. Okay, have a good day, everyone.
Have a good day, อาจารย์
สวัสดีครับทุกคน
สวัสดีครับ